Let's start this chapter on randomized coordinate update methods. The method is based on randomized coordinate fixed point iteration, which we will first introduce. Then we define coordinate-friendly and extended coordinate-friendly operators. The method is computationally efficient when the underlying operator is either coordinate-friendly or extended coordinate-friendly. Next, we provide several examples. And finally, we discuss the potential difference between the theory and the practice regarding speedup. Partition a n-dimensional vector into m non-overlapping blocks of sizes n1 through nm. The sum of n1 through nm equals n. So we can write x as the concatenation of its components, every i's component by seeing Rni. Note that some researchers would write x as a column vector and xi's as subcolumn vectors. Therefore, they use this bracket and semicolon notation to highlight the fact that they are stacking subcolumn vectors into the original column vector. The operator T maps Rn to Rn. Therefore, we can partition the results of this operator also into n blocks. Every block has a size ni. And using this notation, we can define a new operator T sub I as the operator that only takes the i's component, i's block of the results of Tx and maintain all the other inputs unchanged. Therefore, Ti is equal to T on the i's block and equal to identity on all the other blocks. Technically, a block would mean multiple coordinates, and coordinate means one coordinate. However, the difference is insignificant in this lecture, therefore we use these two words interchangeably. Consider the fixed point iteration with operator T. The method of coordinate update fixed point iteration, written shortly as C-FPI, is to first select a block from all the m blocks and call the selected block ik, and then apply tik operator to the current iterate to get the new iterate. By the definition of T sub I, only the ik's block is updated. All the other blocks of xk remain the same. By specifying the selection rule for ik, we'll fully specify the method. There are many ways to select the block to update. They come with different advantages and disadvantages. Here are some common selection rules. In the cyclic rule, one selects the blocks sequentially following a fixed order and cycle that. Although the order can be shuffled, often the order is just chosen as 1 through m. In the cyclic shuffle rule, we shuffle the ordering of the blocks and then select them sequentially. In the next cycle, we shuffle them again and then select them. This is also called random sample without replacement because in every cycle, every block is selected only once. The essential cyclic rule is a superset of rules. As long as every block is selected once or multiple times in every cycle, it follows this rule. This rule does not specify the order and how many times every block must be selected in every cycle. Both cyclic and cyclic shuffle rules are special cases. The greedy rule is a set of rules in which we select the block that leads to the most immediate progress, which can be measured in several different ways. In the randomized rule, we select the blocks randomly according to a certain distribution. Every selection is independent of the others. Let's compare it to the cyclic shuffle rule. This one do random sample without replacement, which means it deliberately avoids selecting a block more than once in every cycle. In the randomized rule, the random sampling is done with replacement, which means if a block is just selected, it is put back and it may be selected at the same distribution in the next selection. So all the selections are independent of one another. Among all the rules, we're going to focus on the randomized rule since its analysis is simplest. Specifically, we're going to get randomized coordinate update fixed point iteration, where we sample IID uniformly from 1 through m, and then update just the ik's component of x using t and keep its all other components unchanged. The main theorem of this lecture is Theorem 2. So consider the theta average operator T with a non-empty fixed point set. Also consider the random block indices that are sampled uniformly, and pick any point at x0 the starting point and use this random block sequence to generate this random coordinate fixed point iteration xk. And then the conclusion is, with probability 1, the random sequence must converge to some fixed point x star. And there are two expectation quantities will be monotonic in k. The first one is the expected distance square of xk to the fixed point set, where the expectation is taken with respect to the entire sequence of random indices. And the second one is the expectation of xk to any fixed point x star, whether it is the same x star as the limit, or in case fixed point t has multiple points in it, any fixed point you can choose. Finally, the distance sequence of xk to fixed point t as the random sequence converges to 0 with probability 1. The main difference between this theorem and Theorem 1 is that we have added this random sequence, and therefore some results now have to have probability 1 as a quantification, and these results now come with expectation. Otherwise, the theorem remains the same as Theorem 1. Next, we present some results and preparations to prove Theorem 2. First, we present supramartingale convergence theorem. A supramartingale is a sequence of random variables, denoted as Vk. Conditioned on all the previous V's, the expectation of the new V is less than or equal to the last previous V. And in this particular theorem, we also assume the supramartingale is non-negative, and Sk's are the random variables that represent the difference. And the result is that the sum of Sk is finite, or Sk sequence is summable, and the sequence Vk converges to some random number of V theta, which is non-negative. As the second preparation, we introduce operator S and operator Si. S satisfies T equals identity minus theta S, or S equals identity minus T divided by theta, and Si has a similar definition. So Si as sub I is equal to the S operator on the ith component and 0 on all the other components. Therefore, the sum of Si operators is S. Note that both S and all Si's map from Rn to Rn. Using this notation, we can express the random coordinate fixed point update as xk plus 1 equals xk minus theta times Sik applied to xk. The next preparation is this fact that T is theta average if and only if S is half coercive. The proof is very simple. By definition, T is theta average if and only if this operator is non-expansive, and this operator is no more than identity minus S by the definition of S. And then using the definition of non-expansiveness, we write out this inequality, which must hold for all x and y in Rn. Expand the left-hand side and cancel the term with the right-hand side. That leaves us with this square term less than or equal to this inner product term that must hold for all x and y. And this defines S as a half coercive operator. By definition, fixed point set of T is the zero set of S, Therefore, any point that is fixed point of t is a 0 of s. Look at this inequality. If we let y be x star, and sy will be 0, and so this disappears, this disappears, that gives us this inequality that we'll use in our proof. The last part of the preparation to prove Theorem 2, let's study conditional expectation. Recall that the I sequence are the indices of the blocks that are randomly chosen to generate the xk plus 1. By definition, xk plus 1 is a random variable that depends only on I0 through ik. The initial point is arbitrary but not at random. We write E for full expectation. That's the expectation with respect to the entire infinite sequence. And we write E sub k as a conditional expectation with respect to ik that is conditioned on the past random variables. However, recall ik is chosen independently of these previous random variables. Using those definitions, we can get some conditional expectation identities. First things, xk is generated before ik is even sampled. We have expectation, case expectation of xk equal to xk self. Then, taking the case expectation on sik of xk, the expectation is taken with respect to ik. And recall ik equals I for equal probability, which is 1 over m. So we have this summation. And then using the definition of S, we get this. Next is similar here, except we now using the definition of square 2 norm. So again, the expectation is taken with respect to ik. So we have summation over I, 1 over m, multiply each possibility. And then using the definition of Si and 2 norm squared, we get this. Now let's start the proof of Theorem 2. Similar to the proof of Theorem 1, there are 3 stages. In the first stage, we expand the distance squares. Now this expansion uses the update formula, and expanding this formula gives us 3 terms, where the last 2 terms involve S sub ik. And then let's take conditional expectation over sik, and the right hand side has a term that independent of ik, and have 2 terms that depend on ik. And using the formula on the previous slide, taking conditional expectation over sik of xk going to give us sxk with 1 over m and ssk 2 norm squared over m. And then using the co-cursiveness, the half co-cursiveness of f that we proved about 2 slides ago, we get this inequality. Now this let us form a non-negative supermartingale over xk minus x star 2 norm squared. So note that we have to first pick a fixed point, then get a non-negative supermartingale on which we can apply the supermartingale convergence theorem. But before we apply the supermartingale convergence theorem, we just take full expectation on both sides of 4 and get this quantity, and therefore this sequence is a non-negative monotonic non-increasing sequence, which means that the sequence must monotonic converge to a number, and this sequence must also, because x star is arbitrary, minimizing over x star, we're gonna get the convergence of this sequence as well. In stage 2, we prove convergence of error rates. Now apply the supermartingale convergence theorem to the sequence in 4, which is this. We get 2 statements that hold with probability 1. In the first statement, S of xk, we're going to call it residual or fixed point residual because S is identity minus t scaled by 1 over theta. So this is basically the square size of the residual at iteration xk. And this says the size of the residual is summable, square summable, therefore the size sequence converges to 0. In the second statement, it says the supermodical sequence self converges to a non-negative number. So it implies that this xk sequence is bounded with probability 1. In stage 3, which we missed the title here, we're going to apply two arguments to get the main results of Theorem 2. The first argument is regarding the sequence. When a fixed point set has multiple fixed points, picking a fixed point x star defines a sequence. And in stage 2, we showed that the sequence converges with probability 1. We're going to apply proposition 1, which we're going to state and prove in 2 slides, to improve the statement into the following. With probability 1, the sequence exists for every fixed point. The subtlety will be explained in the next slide. But other than that, ignoring probability 1, this convergence statement is something we have seen in stage 2 of Theorem 1. So apply the same argument in Theorem 1, we can obtain with probability 1, the xk sequence converges to x star, which is a fixed point. And this proves Theorem 2. Now let's look at the subtleties in stage 3 of the proof. Recall in the proof we first chose an arbitrary fixed point, then argued that the sequence in K is a supermartingale and it's non-negative. Therefore, we can apply the theorem to conclude that the sequence has a limit, and this holds with probability 1. So what does that mean? Well, this randomized algorithm generates an infinite sequence xk, and if we run it multiple times, we're going to generate multiple sequences. So those all possible sequences form a whole set, and we're talking about those sequences such that this limit exists. So we're talking about subset, and this statement says for every x star you form this subset, and the subset has a size 1 or measure 1. If you change it to a different fixed point, you're looking at a different subset. That new subset still has probability 1. Every fixed point generates a subset of sequences, and the size of every one of those subsets has probability 1, has size 1. Down here, in order to apply the argument of Theorem 1, we need a stronger statement. It says that this limit needs to hold for every and all fixed points in the fixed point set. So we're looking at those sequences, not just having this limit exist for a particular one, but all of them. So recall we have one subset for every x star. So we have many subsets for many x stars. And here we're looking at intersection of those subsets. And we take the intersection of those subsets, and we need the intersection still have a size 1. Let's talk about the size of the intersection. When there are countably or finite many measurement sets, taking their intersection, the intersection will still have a measure 1. However, when the number of measurement sets grows to uncountably many, then the intersection may have a measure equal to 1 or may have a measure strictly less than 1. So in our case, what we need to do is to take the intersection over x star in fixed point set T, but fixed point set T may have uncountably many fixed points in it. Therefore, this intersection falls into the second case. Therefore, we cannot directly go from the weaker statement to the stronger statement. We need something else. And proposition 1 will use the property of this fixed point set to show that the stronger statement indeed holds. Now let's look at proposition 1. It states, take any subset of Rn and any random variable sequence, then statement 1, which is a weaker statement, implies a stronger statement. In the weaker statement, for every point with probability 1, the limit exists. The stronger statement says with probability 1, the limit exists for all points in Y. The proof has 3 steps. The first step argues that since Rn is separable and of the subset is separable, so Y is separable means Y has a subset that has countably many points, and the subset is dense with respect to Y. And then, since the subset of Y has countably many points, we can upgrade the weaker statement into the strong statement, except for now we only have for all little y belongs to the subset, the countable dense subset. And then, finally, we use the factor that this function and the sequence is a equicontinuous sequence of functions. Then, because the sequence is equicontinuous, the fact that it has limits on the dense subset can be improved to that it has limits on all of Y, the full set. By equicontinuous, we mean this sequence of functions are uniformly continuous. The second uniform is the standard. It's applied to the points in the domain of the function. That is, for fixed k, look at this function in Y, and it is not just continuous at any point Y, it is uniformly continuous. And then we apply the continuity across different k, and it's also uniform over k. Now we leave these the actual proof to the reader. It is documented in the chapter. So next we introduce coordinate-friendly and extended coordinate-friendly operators, as these operators are computationally efficient. The motivation is Theorem 2 only proves convergence, but random coordinate fixed point iteration is only useful if it's computationally efficient, and it's computationally efficient when the underlying full operator is either coordinate-friendly, which we're going to define below, or extended coordinate-friendly, which we're going to define in a few slides. So consider a partition of point into m disjoint blocks. We say a mapping x to z is coordinate-friendly if the worst cost of computing a block of z is much less than the cost of computing all the blocks of z together, where much less than depends on the context. And we say an operator is coordinate-friendly if x maps to tx, that is, compute one mapping under the operator is coordinate-friendly. If computing a mapping is coordinate-friendly, then using sufficient number of processors, we can assign every processor to compute a block of zi, and the longest time to finish a block is the parallel processing time. By coordinate-friendly, this time is much less than the single thread time of computing the whole block. Therefore, this mapping is parallelizable. Affine operators or linear operators are coordinate-friendly. Consider this affine operator that multiply x by matrix A and plus vector B. The cost of this calculation is proportional to the number of rows in A or the entries in B. So if we partition A into block of rows, and then the cost of calculating one block is proportional to the number of rows in that block. So as long as the maximum number of rows is sufficiently less than n, this operator and this mapping is coordinate-friendly. Separable operators are likely coordinate-friendly. We say an operator is separable if calculating the operator breaks down to calculating m independent operators. So if the worst cost of calculating those smaller operators is much less than the cost of calculating the entire operator, then this operator T is coordinate-friendly. There are common examples of separable operators. The simplest example is a linear transform represented by a block diagonal matrix. And this is coordinate-friendly if all the blocks are sufficiently small. F is a separable function if it can be written as sum of fi of xi, i.e. every fi depends on only one block and a unique block of x. If f is separable and differentiable, then its gradient is separable. It's a separable mapping because the gradient decomposes to gradients of individual fi's. If f is separable and CCP, then its proximal operator is separable because it decomposes into the independent proximal operators of every fi's. Hence, if all the fi's are easily differentiable, or all the proximal of fi's are easy to compute, then the gradient and the prox of f are coordinate-friendly, respectively. We say a constraint x belongs to C is separable if every block xi belongs to a separate set Ci. Then projecting onto C decomposes into a sequence of independent projections onto the Ci's. The simplest example of separable constraints is the box constraint, where every xi has its own lower bound and upper bound. Coordinate-friendly operators, although parallelizable, are quite limited. And here we introduce a much bigger set of extended coordinate-friendly operators. A operator is extended coordinate-friendly if there exists an auxiliary quantity y that depends on x such that over the worst coordinate, the cost of updating x over that coordinate or over the block and updating y correspondingly is still much less than the cost of updating x to tx. In other words, computing just a coordinate with y of x maintained is efficient. Quantify this operator as extended coordinate-friendly. To introduce examples of extended coordinate-friendly operators, we need to extend the coordinate notation. So given a m partition of the entries of x, we correspondingly partition the columns of A matrix into this form such that the i's column block has ni columns in it. Therefore, we can write A as the combination of the column blocks and A times x as the sum of the ith block multiplied by the ith subvector of x. When f is differentiable, we partition the entries of the gradient of f accordingly, such that i's subgradient has ni entries. We use this example of gradient descent on least squares to illustrate the usefulness of the extended coordinate-friendly operator. Consider this least squares problem and its gradient descent operator. To compute this operator, we do A times x followed by subtraction of b and then left multiplied by A transpose and then left multiplied by scalar alpha and subtracted from x. We claim T, this operator T is parallelizable but not coordinate-friendly. However, it is extended coordinate-friendly. To verify the claims, let's calculate the serial cost of update and parallel cost of update. Recall the matrix has R rows and N columns, and this operator is dominated by two matrix vector multiplications, one by A and the other by A transpose. Therefore, the serial cost is ORN. The parallelizable cost is ORN divided by P, since every dominant step, matrix vector multiplication, is parallelizable. However, this operator is not coordinate-friendly. The reason is that in order to calculate Ti, the ith block of T, we would have to first calculate A times X. Although given A times X, Ti of X can be calculated in the cost proportional to Ni, the size of the ith block. Calculating A times X itself already costs Rn, which is already similar to the cost of calculating the entire T. However, T is extended coordinate-friendly by maintaining Ax in memory. So given Ax, to update X to T of X, previous slide has calculated the cost is O Rni. Now the cost of updating Ax to A times the vector Tix, we only need to add the difference to the vector Ax. And the difference is can be calculated by multiplying the ith column block of A to the subvector difference. And this cost Rni, and this addition cost R. Therefore, this update to Ax also cost O Rni. Together, updating both quantities cost O Rni. By applying this idea, we obtain the following coordinate fixed point iteration with operator T. First of all, we can initialize X, and we have to initialize Y corresponding to A times X. A simple approach is to set it to 0 vector and Y also to 0 vector. Then at every iteration, we randomly sample a IK and then update IK's block using YK, where YK equals A times XK. And the unupdated blocks should cause no operation. And then to Y, we need to update by adding the difference to it. The difference given by this matrix column block multiplied by this difference. So this step, once again, this step cost Rnik, and this step cost Rnik. Altogether, each iteration costs ORNIK flops. There's a different approach to calculate the gradient operator by first pre-computing A transpose A and A transpose B, but this approach is not effective, not computationally effective if R is less than N or R is roughly equal to N. First of all, pre-computing this matrix and this vector costs ORN squared. When N is much greater than R, and this cost can be prohibitive, you may run into out-of-memory issues. Now, even if you can pre-compute A transpose A and A transpose B, given these vectors, and given this matrix and the vector, calculating the new ith component already cost ON and I, which is at least not smaller than OR and I, since R is less than N. Of course, if R is much greater than N, and you can pre-compute A transpose A, then calculating the gradient descent operator boils down to calculating matrix vector multiplications. And this is coordinate friendly if the matrix is pre-computed. Next, we provide some more complicated examples of coordinate friendly or extended coordinate friendly operators, some of which are not that obvious. Our first example is coordinate gradient descent. Consider minimizing a differentiable function. We apply RCFPI to the gradient descent operator. It amounts to choosing a block of coordinate, and update that block. And this method is called randomized or stochastic coordinate gradient descent. According to our theory, it converges if a minimizer exists, f is L smooth, and step size alpha is no more than 2 over L. In general, the gradient descent operator may not be extended coordinate friendly. However, it is in many machine learning training setup. Consider a linear model A transpose X minus J. We collect R samples, and ideally, for every J, A transpose X should be close to Bj. So we measure the difference in this way using a set of differentiable functions. And we stack all the AJs and introduce this total loss function, which is the separable sum of individual loss functions. RCFPI gave rise to this randomized coordinate gradient descent method, where we maintain y as ax in memory. To update the I-case block of x, we calculate the block coordinate gradient, and which equals the transpose of the I-case column block of A multiplies grad L of yk minus b. Now, if every derivative of Lj costs O1, then the total cost of this step is OR. Then in that case, the bottleneck of the first step is this matrix multiplies the vector, which costs ORNIK. The bottleneck of second step is also ORNIK. Therefore, if all the ni's are small, this method is coordinate friendly and can be parallelized. Note that we have to maintain y equal to ax, the initial x. We're missing a 0 here. In this next example, we generalize coordinate gradient descent to let different blocks have different step sizes. Consider minimizing an L-smooth function f of x. Introduce this diagonal matrix, where in the i's block, the beta is beta I, and all the beta i's are strictly positive. With a free x, the expressing power of dx is the same as that of x. Therefore, we obtain this equivalent problem. Now, applying randomized coordinate gradient descent method with step size alpha to this new problem, we can write an equivalent update formula on x, where the updated block ik now have a different step size that equals alpha times bik. Since bik's can be different, every block may have its own step size. Now, this non-uniform blockwise step size is often important for you to obtain a speed up compared to the standard full deterministic gradient method. Because even though the value of f depends on all the blocks of variables, the value may be less sensitive to some of the blocks. Now, those less sensitive blocks, they can have larger beta I, which often give you a speed up. In this example, we introduce coordinate proximal gradient descent method. Consider minimizing a smooth CCP function plus a separable function, where the separable function, in the separable function, all GIs are CCP and proximable. Apply the forward backward splitting operator to this problem yields this proximal gradient operator. The coordinate version of this operator uses the fact that G is separable. So to update the I-case block, we only need to calculate prox of GIK applied to its input. And this input takes the I-case block of identity and the I-case block of grad F. Altogether, we obtain this coordinate proximal gradient descent iteration. Now, this iteration converges if a minimizer exists, F is L-smooth and CCP, and all GIs are proximable and CCP, as well as requiring alpha less than 2 over L. Like before, we can apply a blockwise argument to generalize this method to let different blocks that have different step sizes. If G is not separable, then prox alpha G is not separable. And to obtain the i's component of this operator, we may have to calculate an entire alpha G, which requires the entire input. So in general, in this case, this proximal gradient operator is not extended coordinate friendly, and the corresponding randomized coordinate fixed point iteration is not computationally efficient. Next, we introduce stochastic dual coordinate ascent in a machine learning setup. Consider this problem where G is strongly convex CCP, so G star, the convex conjugate, is smooth, and all the Li's are CCP and proximable. Form matrix A and vector B, then the primal problem can be generated by this Lagrangian, and for fixed U, minimize out X, give us the dual objective, and the dual problem is to maximize over U. In this problem, this part is smooth, and this part is separable and proximable. Apply randomized coordinate proximal gradient descent method to the dual. In every iteration, we update one block of the dual variable U. We have used the fact that the proximal of a separable function is separable. We have used the fact that G star is smooth, we can compute its gradient. And we have maintained y equal to negative A transpose U, therefore we also need to update y. In this iteration, the dominating computation is the gradient, the matrix vector multiplication, another prox, and matrix vector multiplication. If the gradient costs OR and every prox costs O1, then the dominating parts are the matrix vector multiplications. With YK maintaining memory, this update operator is extended coordinate friendly, and this RCFPI iteration is computationally efficient. Finally, we can recover the primal solution X from grad G star. Perhaps you have noticed that in primal coordinate gradient descent, updating each primal variable block requires access to the corresponding column block of A. In dual coordinate gradient descent, to update a dual variable block, we need access to the corresponding row block of matrix A. Now, in machine learning, every row corresponds to a training sample, so we may not want to split that sample into smaller parts. Therefore, the dual approach is preferred because it does not break a row into smaller parts. In this example, let's look at MISO or Finito algorithm. Consider minimizing a CCP function R plus the average of smooth and CCP function F1 through M, and use the consensus technique, that is to introduce vector xi for every fi and ask all of them to equal, where C is the consensus set, onto the indicator function. Note that we have multiplied the objective by M, so we end up having an R for every xi. To apply operator splitting, we split these three terms into two parts. The first part is separable function of fi's, and the second part is indicator function and the sum of rxi's. Although this function is non-separable due to the indicator function, it has a simple prox formulation from the previous exercise. That is, no matter what input is, the output is a vector where all subvector x equal one another and equal to prox r of the average of the input yi's. Interestingly, both forward-backward splitting and backward-forward splitting are extended coordinate friendly when the average of yi's are maintained and they are equivalent. Let's compare the two. The forward-backward operator applies the backward operator prox and then forward operator gradient descent. The forward-backward splitting operator applies gradient descent and then a prox. The random coordinate version of backward-forward apply updates to zi. The random coordinate version of forward-backward splitting apply updates to xi. Now, to apply update to zi, we basically take out the i's component of the forward operator, which requires the input of the i's input of the prox. So this is the i's input of the prox. Recall that all the i's entries of the prox is equal. Then we update zi, and then we have to update the maintained average of the zi's that account for the difference, the change in the i's block. In the random coordinate version of forward-backward, yes, we first apply xi. We need to update the xi, and update xi requires all the inputs of this part. However, the input is maintained as the average of the yi's, and to update the average, we have accounted for the difference in the yi's. the two iterations are equivalent. In fact, we can plug in zi update into the z-bar update, and then we're going to arrive at the second iteration. So these two iterations are called minimization by incremental circuit optimization, or MISO, and independently invented in another paper which called the method Finito. Those methods converge if a solution exists and alpha is less than 2 over L. Once again, we can make a non-uniform step sizes for the blocks. Among the equivalent two iterations, backward-forward iteration has a minor and subtle advantage. Recalling backward-forward iteration, the main iterator is z, so we can simply set all the zi's to 0 and the average of z to 0. In forward-backward splitting, the main iterator is x. Regardless of how simply we set the x, we have to calculate this to maintain the average. This requires calculating the gradients, so this is extra computation. In this example, let's consider conic programs with many small cones. We minimize the linear objective, subject linear constraint, and the set constraint. This writing means that the subvector xi lies in the corresponding set qi. When these sets qi's are convex cones, the problem is called a conic program. We also assume A has rank R. Otherwise, this linear system either has redundant constraints or is infeasible. We assume the cost of projecting onto every set qi is ci. So we write constraints using delta functions into the objective, and then we create two functions for the objective to which we apply DRS. There are two orders, and in this application, we first do the prox over G and then the prox over F. Prox over G is separable because the set is separable. Prox over F requires a matrix, a vector multiplication. There is a matrix, involves certain inverse, and the vector V also must be pre-calculated. See a previous exercise. Applying random coordinate API to this DRS operation, we're going to calculate all the x, update all the x, and only update one of the zi block. So updating all xi's can be parallelized, and updating a zi block requires the corresponding block of the D matrix which we pre-compute. The cost of this FCFPI iteration is the sum of ci's plus n times nik, the size of the row block of the matrix D. This iteration is extended coordinate-friendly by maintaining yk like this in memory. To update the ik's block, we only need the ik's block of y as well as the latest refreshed the ik's blocks of x. To update y, we need to account for the changes in that we have applied in x and z. When a conic program has a large cone, the cost of projecting onto the cone ci can be much larger than the cost associated with other cones. A huge ci can stand out and make parallelization difficult. However, this is not the case with a second-order cone. A second-order cone is a subset where xn is greater than the Euclidean norm of the first n-1 components. When n is 3, the shape of this cone is an ice cream. When n is 1, it just says x1 is greater than x0. Therefore, a conic program with a second-order cone is called a second-order cone program, which is a generalization to the linear program. Consider an arbitrary point where u is the first n-1 component of x and t is the last component of x. Projecting this point onto the second-order cone reduces to just scaling the first n-1 components by the same number of row and scale the last component. When this inequality holds, rho and sigma are 0, 0, which give you the origin. When this inequality holds, it returns you the same point because the point is inside the cone. Otherwise, you have to calculate this. Note that this calculation, the main cost of this calculation is taking the true norm of the first n-1 components and scaling the entries. Consider a conic program with one large second-order cone, where A has rank R. We only use one cone for simplicity. The argument below applies to any conic programs with one or multiple large second-order cones and small of the cones. Apply Douglas-Rushford splitting to this formulation. Recall, to apply DRS to this Conic program, we need to pre-compute this D matrix and this V vector. And we partition ZK into subvector UK corresponding to its first n-1 component and its last component. Similarly, we partition D into column blocks where G has the first n-1 columns and F is the last column. Applying random coordinate DRS boils down to updating ZIK at a low cost, and this requires calculating XIK as well as updating two maintained variables. The first maintained variable is actually norm of UK, and this norm can be maintained when IK is chosen as one of the first n-1 components using this formula. And otherwise, UK does not change because the update is applied to the T component. And similarly, we have to update the maintained variable GUK. And this implementation costs ON flops per iteration and is coordinate friendly. Finally, let's discuss some points. Randomized coordinate FPI or RCFPI may provide a speedup over standard FPI when the operator is coordinate friendly or extended coordinate friendly. And you're very likely to get a speedup when the coordinate y step size are larger than the step size used in FPI. When comparing RCFPI to FPI, it's useful to compare one iteration of FPI with one epoch of RCFPI, that is m iterations of RCFPI. Now, given coordinate friendly or extended coordinate friendly structure, one epoch of RCFPI and one iteration of standard FPI have similar computational costs. Looking at Theorem 1 for FPI and Theorem 2 for RCFPI, they guarantee a similar amount of reduction in fixed point residual if we compare one iteration of FPI and one epoch of RCFPI. However, RCFPI and FPI both may converge much faster than what the Theorem 1 and Theorem 2 guarantee because they are worst-case guarantees. Now, if so, the similarity in the guarantees in those theorems does not really mean much on the similarity or difference of the actual performance. The ability of using larger step sizes for different blocks often, so not always, translate to a speedup. There are cases where the step size limitation causes the bottleneck of the algorithm, therefore alleviating the bottleneck leads to a speedup. In some cases, there are even theoretical support for this observation. For example, applying different step sizes to different blocks and can let an epoch of the randomized coordinate gradient descent method achieve a greater reduction in function value than an iteration of the standard gradient descent method. However, this requires using the subgradient inequality in the analysis rather than just the monotonicity inequality. In general, RCFPI may not offer a speedup over FPI. There are cases where an epoch of RCFPI and an iteration of FPI make the same progress. They converge at the same actual rate. However, we are not aware of any examples where an epoch of RCFPI give less progress of an iteration of FPI. Now, studying RCFPI without any guarantee of speedup still serves as precursor to the asynchronous FPI that we will discuss in Chapter 6. Asynchronous FPI will achieve more per unit of time.